This lecture demo is about Kirchhoff's law, which is one of the approach in solving problems in an electrical network. The first law under Kirchhoff's law is a current law. Uh, the law states that the algebraic sum of all currents in a junction of an electrical network or circuit is zero. And to perform algebraic summation, we have to use sign convention that all current entering the junction is considered positive. The junction is an interconnection of three or more branches eh, of an electrical circuit. In the figure shows a junction A having 5 branches interconnected, and there are 5 currents. The current I1, I2, and I3 are current entering the junction A, while current I sub 5 and I sub 4 are currents leaving the junction. And so therefore these I sub 1, I sub 2, and I sub 3 are considered to be positive, and the current I sub 5 and I sub 4 is considered negative. Then summing this up and equate this to 0, we can rearrange the equation, and we can see that all the current that enters the junction shall be the same current that will leave the junction. So current that enters is the same current that leaves the junction. That is a current law. Another law is the voltage law under Kirchhoff's laws. The voltage law states that the algebraic sum of all the EMFs, these are the voltage source, all the sources in the voltage sources in the circuit, and the I times R drop. This is a voltage in the R. In any closed loop on an electrical network is 0, or summing up all the voltage rise, which is positive voltages, and summing up all the voltage drop, which are negative voltages, in a closed loop must be equal to 0, or the voltage rise and voltage drop are equal. What are the voltage rise and voltage drop? Voltage rise is said to be positive for EMF or source. It is positive when we go through a battery or any voltage source from the negative to positive terminal of the source. going through, meaning this is the loop direction. This is the loop. So we go through a loop, a closed loop, and when we traverse into this battery from its negative terminal to the positive terminal is positive or voltage rise. So meaning if we end up or leave the battery at the positive terminal, it is positive. Now another voltage in a circuit is due to the flow of current in a resistance, and that is the I times R. So whenever there is R and a current flows into that R, we have to consider this in the summation of the voltages, or the KB, summation of the, or applying the KBL. So the I times R is rise or positive when going through this R following a loop direction from the negative to the positive terminal of the voltage across the R. So the R has a voltage because there is a current that passes through the R. Or going through R in the opposite direction of the current. Say we have here R, this is the R, and we have here the current going downward. If we are going to determine the polarity of the voltage in the R, which is I times R, so this is I times R, which is the voltage across the resistor, and the current enters into this terminal. From where the current enters, the terminal is positive for R, and the terminal of R from where the current leaves is negative. So this is the voltage across, the polarity of the voltage across the resistance. So if we go from, this is the loop direction, we are going through the resistance in a direction from the negative terminal, leaving the positive terminal. This is the loop. The I times R is positive because we leave the positive terminal of the voltage across the R. Or we are opposing the direction of the current I that passes through the R. What are the voltage drops? For EMF or voltage source, any voltage source, if we go through a battery following a loop direction from the positive leaving the negative terminal, the E is negative. For the IR, if we are going through a resistance where we enter at the positive terminal and leave the negative terminal, this is positive because the current enters at this terminal, so this terminal is positive, and the current I leaves this terminal, so this is negative. Now this is the loop direction we go through. The R from the positive terminal of the voltage across the R and leave the negative terminal, the I times R is negative. Or if we go through the resistance in the same direction with the current, the I times R is negative. Let us consider this circuit having one loop. This is one loop, this is a closed loop. And let us name this as A, B, C, D. This is the loop, the name of the loop. We can have here a loop of as A, B, C, D, A. That is a closed loop. Or we can have a loop in a reverse direction, loop A, B, C, D, A. That's also a loop. It is the same loop, but the direction is counterclockwise. This is a clockwise direction of loop. This is a counterclockwise direction of the loop. Let us consider a clockwise direction of the loop and apply the Kirchhoff's voltage law. So loop, let us consider loop A, B, C, D, A. Let us establish the polarity of the voltages in all the elements. The E, it is known that this short plate is negative and the larger plate, the longer plate, is positive. And the voltage across R1, which is B1, the current in the circuit is I, which is directed into this towards R1, and it enters at this terminal, and so therefore this terminal is positive. It leaves at this terminal, and so therefore it is negative. Then in R2, it enters at this terminal, so this terminal is positive and the other terminal is negative. So the current goes into the direction from the battery and goes back to the battery. Now, let us apply KVL. So apply KVL at loop direction A, B, C, D, A. So A to B, what is the voltage? A to B, the voltage is positive E. and B to C, the voltage is negative V1 because we leave the negative terminal. Here we leave the positive terminal. Then B2, we enter the loop is C to D. C to D, we enter positive, we leave the negative terminal, and so therefore this is negative V2. And then going to A, no voltage in this part of the circuit, and the loop is closed. We start with A, we go back to A, the loop is closed, and so therefore equated to 0. Now let us replace B1 and B2 in terms of current and its resistance. So E1 minus B1, which is I times R1, minus B2, which is I times R2, and this is equals to 0. If we are going to rearrange this equation, we can have E1 is equals to I times R1 plus R2, which clearly shows that the voltage supplied is equals to the voltage across the R1 and the voltage across the R2, which is simply written as I times R total. If we are going to sum up the R1 and R2, which is coinciding, confirming the Ohm's law. Let us apply the